having some multiple choice questions on the exam. I think it was D. But so I was like wondering how would that even work, right? Like, because I'm guessing one way that would work is if you would get credit for the problem if you showed your work. Then, if you got the multiple choice right, you know, you get full credit. But if you don't, if you're just guessing, right, and you just happen to pick the right answer, would you get credit for that? Do you see what I mean?
Yes. If you don't get credit for that, then what's the point of making a multiple choice? Right? Because
well, yeah. So the idea, I think, and correct me if I'm wrong, but I think the idea behind having a multiple choice is that if you went the wrong direction, then you can do some self-correction, or to give you a hint of what kind of direction you should go.
yeah, I suppose. I always thought that it was a way to reduce strain on the instructor for grading.
Yeah, like this is Scantron.
Yeah.
It's just speeding through a machine. Yeah, I'm pretty sure that has been the case. But for this kind of class where you're being graded on your ability to understand like what's going on and how to formulate these answers, and we have lots of equations to deal with, lots of formulas. You know, like what's the best way to deal with that on an hour exam when you have 10, 12 questions.
What if you gave us the problem and an answer and we had to get in between?
Wait, what?
You gave us the question and then the final answer, and then we had to show you.
Oh, do the image. Oh, like one of those problems where it says, show this.
Yeah,
like,
show how you get to this answer.
Oh, wow.
That was a joke.
Those are horrible.
Like one of those proof kind of, those proof kind of
no.
questions. I always had difficulty with those proof questions. So
Don't do that.
So, okay, so if we did have some multiple choice questions, would you guys be okay with that? I mean, is that helpful or kind of, I mean, because I guess the thing is that if you got the multiple choice question wrong, you would still get partial credit for any work that you did do, right? So that's still in effect. So I guess the only thing is that the partial, I mean, that showing you a variety of answers will allow you to self-correct or allow you to know what direction to go if you were a little confused about the question, like what the question is asking you to do, maybe. I mean, is that how you guys view multiple choice questions? Is that
in the pet?
as long as I do the multiple choice questions right? No making any mistakes. Oh wait, so maybe I should have like an extra question that says none of the above.
Oh.
I mean, because I make mistakes too. So.
The way that New did it in Digitron was like the multiple choice would be like factual, conceptual things, and then the short answer would be actual like calculation stuff. But like he would never make the multiple choice, or the majority of the multiple choice were like about facts concerning certain elements of whatever we were learning at the time. If that makes sense. Like it wouldn't be find the right answer, it would be given this set of information, what can you say about maybe like the op-amp? Maybe. Does that make sense?
Yeah. Wait, so is that multiple choice though?
Yeah, he would make those multiple choice where it'd be like, what is a characteristic of this thing? Or if we have this many electrons here,
Oh, I
what
see
can
what
you
you
say
mean.
about like the charge of it and that sort of thing.
Okay.
Like
Okay.
a full wave rectifier, and he would tell you which LEDs would be on.
Yeah, that
You
sort of
could
thing.
do stuff like, In
Where
some
it'd be
situations.
like,
Heat injection, you would
It's
say these are
conceptual,
like
right?
the
Yeah, conceptual is
characteristics of it, with the electrons flow this way or that way, with the negative on this side.
Okay, so he's like, so those aren't really like workout kind of questions,
No,
but
just like
conceptual kind of
conceptual.
questions. I see, I see.
you don't have to do that though, if you don't
Yeah.
want to.
Okay.
Please don't.
So would you guys rather not have any type of multiple choice questions on the exam?
Yes.
Wait, yes that you do, or yes that you don't?
Yes.
We're fine with that.
Yeah.
Okay.
You don't have to.
Okay.
Thank you for.
Okay, well, just considering, no comments that were made by you guys, so, I need to get that feedback.
If you do put multiple choice on there, you could weight it to where actually getting the circle right is only worth like a fourth or a fifth of the points for the problem, and the rest comes from showing work.
Oh, you mean like how to, like deal with the partial credit?
Blindly guess this gets them all right, they only get 20 or 25.
Yeah, that's an interesting question. Like what would happen if they guessed it right, but they showed some work, but didn't really show how they got the answer, right? Yeah, how do you deal with that? Or even another issue that they did the work and they accidentally answered the question incorrectly. Because that happens too, where you want to circle B, but you're accidentally circling C for some reason, you know. If that happened, then they should get full credit because they worked it out, because that's obviously a mistake. But another situation where they're totally going the wrong direction, but then they answered it correctly. Okay. Well, yeah, so if you guys don't want to experiment with multiple choice on an exam,
Okay, look at it is, anything before like homework 6 is, anything before homework 6 is pretty easy, but now we're getting to the more, circuit level stuff, so it's,
yeah,
it's gonna, funk.
yeah, and also if the multiple choice form is a little more, like especially if the answer is an analytical result, you know, there are more than one way to express an analytical result, right? And so it may not exactly look the same on the surface, but if you work it out, you'll see that it is the same. And who's to say that I'm going to choose the way that you're going to choose when you just have, you know, a symbolic result? Okay, so this is the last part of chapter 11 from Interpret A. So lecture 12. Okay, so for review, we went over input biases and offset currents, right? So here's the these input biases right here that go into the op amp to turn on these, you know, the components inside. So you have lots of maybe BJTs in combination with FETs inside of those. The difference between the two of the non-inverting and inverting is the offset current. That's the difference between the two. Okay, and so there's going to be some error that gets generated out here because of that, and you can reduce the error by, one way of doing it is by choosing what this resistance is right here that's attached to this one as this input bias is going on in there. So that's one way of doing it. A couple of problems that you can have, or one problem you can have is that you can have some saturation that goes on if you're, for example, if you have like a system like this where the voltage offset and the current offset is causing current to go through around here and charge up your capacitor. So by the time you're ready to use it, your capacitor is fully charged, and you want that. So you can have like a reset switch. And we also talked about common mode rejection ratio, where the differential mode input, what we're typically familiar with is like the differential input is just a difference between these two voltages, and the common mode input, is the average of the two. Okay, and you can describe it like this, where this output is a function of the gain of the amplifier times the differential input right here, plus this other gain, this common mode gain, times the common mode input, the average of that going in. And then you pull out the gain of the amplifier, then that ratio that's left over right here, which is A over the gain amplifier and the common mode gain, that ratio is the common mode projection ratio. We also looked at this in chapter, on lecture 11. We looked at the frequency response of these amplifier systems. So remember, the amplifiers can be considered as having some overall resistance and also some effective capacitance. Even though there might not be explicit capacitances in there, there's going to be capacitance to each element to ground. And you can model that by having at every node having like a little tiny capacitor, with a small value going to ground. But that's an RC kind of circuit, okay? So that poses a problem. So it means that these amplifiers, they are frequency dependent, okay? And for a general purpose type of op amp, it typically has like a low pass kind of response, but there are others, types too, but it's like a single pole low pass response. It takes on this kind of form right here. And so it's low pass because over at close to DC at zero frequency right here, you just have your regular gain, but as the frequency increases, it gets to the cutoff point right here, it then starts falling off at 20 decibels per decade. Okay. And we also, for the nomenclature, we had these labels for open loop gain, open loop bandwidth of the amplifier, and omega t, the unity gain frequency, right? And that's the frequency at which the magnitude is 0 decibels, or just equal to 1. And also the gain bandwidth product, which is the magnitude and the frequency, which is this omega t, the unity gain frequency. We also looked at the differences between inverting op amps and non-inverting op amps. So here's the ideal situation right here between the inverting and non-inverting. And we also had this look at this table for the non-inverting and inverting. Look at different kind of things like the DC gain, seeing what the differences were, the feedback error, beta. Look at those differences. Bandwidth is functionally the same, and input resistance, how they differ, and also output resistance. We also looked at a macro model. And so these are the kind of models that are in SPICE, right? Because like we were saying, there's like 20 to 100 types of components in there. And so what you want to do is, instead of modeling each one individually and making your circuit take a really long time to simulate, what you can do is just capture the overall effective performance by modeling it like this part in here, like an RC circuit, okay, where it has some effective resistance, some effective capacitance, and you can tune that with the parameters of the macro model. They have lots of macro models like this, not just for the op amp, but for many different kind of components inside of like SPICE and multisim and things like that. And we also looked at higher order systems. So this is like a 2-pole type of system right here, and it has like a band pass type of spectrum. Frequency response. Okay, so we're going to finish up this last section, section 1114, and look at stability of feedback amplifiers. Okay, so we left off with this. We just got into Nyquist. Okay, so what we found out from Nyquist is that it's a way to qualitatively look at stability for feedback systems. And a system that has a form like this, now AS can be all kind of things, right? But if the system is in this kind of form, we could model it like this. Here's the S plane, and here's the T plane, right here. Where this axis right here is the real part of T, here's the imaginary part of T. And what Nyquist found out is that you could just like go up and down the imaginary axis and pick your values of omega, and then what you can do is plot out these lobes right here, where, for example, this crossing right here is when omega is 0, right? So that's what that's going to be. And then as omega is getting smaller from 0, you'll sweep around this direction. And as omega gets larger, you sweep around this direction. And the question is like, if this point right here, where t equals -1, like real, like, because that's where you have this pole, and that's where you have your point of instability. So if this lobe encompasses this point right here, then you know for sure that your system is stable, is an unstable system. And we'll find out today that if your system becomes really close to this, then it can have some interesting behaviors. It won't really be unstable, but it'll, you want to know, like, its behavior, and you can tell what this behavior is going to be, where it's like almost stable, but it's not really quite stable. But it seems like it's, it has this thing called overshoot, and we'll look like that today too. We'll also examine what has to happen to this system in order for these lobes to to encompass this point of -1, t equals -1. Okay, so let's look at first order systems. Then we'll look at second and then third order systems. Okay, so the first two are stable. The third order system could be unstable. Okay, so for first order systems like this low pass single pole amplifier with resistive feedback, it has this kind of form. And so when we say resistive feedback, what we're talking about is where beta is comprised of resistance types of terms, and they're independent of frequency. Okay, and it's constant. Okay, so it has this kind of form, and we can combine the amplitude gain, the amplifier gain, and the loop gain together to get this right here, right? And so if we look at it in terms of just j omega, and we have this form right here, and right here, what I'm doing is I'm breaking it into components of the real part and the imaginary part. Okay, where this is the real part, here's the imaginary part, and we're plotting it out. So this is in terms of different values of t0, like t0 equals 5, is this one right here, t0 equals 10, is this circle right here, and t0 equals 14 is this right here. And all the values of omega being 0 are given as well. Okay, so that's where you can see like the size of the lobe. Okay, but as you can see here, here's your t equal -1. No matter how large these get, you can clearly see that they're not going to encompass this value of t equal -1. So those are always going to be stable. Okay, so if you have an amplifier like this, you don't have to worry about it becoming unstable. Okay. Now for nomenclature, this t0 is t with the frequency of 0. When frequency gets very large, okay, this function right here becomes like this, okay, and you can see that where if this gets very large, the 1 becomes insignificant, and so you have square root of omega being on the bottom, and that really gets large, and so this whole term goes to 0. But this term right here, when this factor and this factor get large, they cancel each other out, and so you're just getting. Wait a minute. That is square, but that's square rooted. So it seems like they would cancel each other out, sort of. Kind of weird. I'm not seeing something right here, but let me check this out to make sure this is correct, but I'm not seeing that. Because it seems to me that when the numerator and denominator, when the omegas get very large, this term will cancel out with the denominator.
It should approach 1 as that gets arbitrarily large.
Huh?
I said it should approach 1 as omega gets arbitrarily large.
Yeah. So, yeah, let me check that one out. Okay, so as omega increases, the magnitude of t approaches 0 and the phase becomes negative 90 degrees. So that corresponds to like, as omega gets, large going around this direction right here, the phase of t becomes negative 90, and that's like the angle pointing out this direction right here. Yeah, and beta, this is just like a scale factor. So as beta changes, this DC value is scaled, and the radius of the circle also changes. But again, it doesn't get to, it doesn't encompass this t equal negative 1. Okay, so anyway, for second order systems, it's like a 2-pole amplifier with resistive feedback, and has this kind of form. And as you can see, it's a second order down here, where if you were to multiply this out, factor it out, you would end up with an s squared down there. But here you can clearly see that now the lobes are like sort of like crossing over into the left half plane right there. Okay, so for this at DC, right, 0 frequency, you get your t equals 0 right there. And for omega being very large, this right here becomes this kind of form, where that's squared, so you just get something like that. But if you look at the magnitude of these things, as omega increases, the magnitude of t approaches 0, and the phase approaches 180 degrees. Now, even though it approaches 180, it doesn't really get there, right? So if you look at this angle right here, it doesn't really get to that point. It gets arbitrarily close to t equals negative 1, okay? But it's still considered to be stable. Okay, and so let's look at phase margin, because this gives you like a better idea of measuring stability, or the onset of instability. So the phase margin, phi m, that's this value right here. That is the angle of the loop gain at omega 1, and omega 1 is the frequency at which the magnitude of that is equal to 1. So it's a particular frequency, okay? So the angle when the magnitude is equal to 1 minus negative 180 degrees, or 180 degrees plus that is the phase margin. Okay, so we're talking about this. So this value of phi is from here to here, right? And this value right here is from here all the way over to here. That's that angle. And you can see where, this right here is like going through, where this is like the unit circle, so it's crossing right there. And so it's just that angle for the phase margin. Okay, but that point right here is the t equal negative 1. And so if this thing kept on getting closer and closer, where this line right here got closer and closer to negative 180 degrees, you can see what we were talking about last time, where it's going towards being unstable, but it never quite really gets there. Okay. So the phase margin is a maximum increase in phase shift that can be tolerated before the system becomes unstable. So what that means is that this angle right here, you have basically this angle left in phase before it becomes unstable. So it tells you how much margin you have that phase. So what happens is first you determine the frequency for which the magnitude of the loop gain is unity, corresponding to the intersection of the Nyquist plot with the unit circle. Okay. Then determine the phase shift at this frequency. The difference between this angle and 180 degrees is the phase margin, just right here. So small phase margins cause excessive peaking and closed loop frequency response and ringing and step response. So that's what I was talking about before. So it does start to behave, in a way that's almost stable, but it's still stable. And here's an example of that. So let's say you have a system like this, and it's a step, and let's say this right here at 1 is the final value. Okay? Now, if you have a very small phase margin, it's very small, you'll get this ringing right here. And it'll have a huge overstep way up here. I mean, it's only going to 1, but because it's like going towards instability but never really quite gets there, it seems like it's trying to blow up, right? So you have this, this huge overshoot before it then starts settling back down. And we've seen this before, right? When we had looked at, when you guys in another class looked at stability, damping systems, right? Where this right here is the damping coefficient. So if the damping coefficient was equal to 1, it's critically damped. If the damping coefficient is less than 1, it's underdamped, like in these cases right here. Critically damped is when it equals 1, and then when the damping coefficient is greater than 1, then it's overdamped. Right here, it takes a little longer to get back. Oh yeah, and critically damped, that's the damping coefficient for which you have the fastest rate of return to where it's supposed to asymptote to. So this right here is the fastest way you can get to the final value. This right here, it kind of like rings down and eventually gets there. This one takes its time to get there, but this is the fastest route to get that point. Now, this table right here, it talks about the overshoot percent. Like this one right here is like 25, so it overshoots by 25% of where it's going to end up. And it tells you what that phase margin is in degrees. It's 40 degrees right there. And it gives other values too. But
So what is that a graph of?
oh, this is like if you're having if you're looking at your angle, so this is omega times t, right? So if you're looking at your angle or like your a good way to think about this is like okay, so let's put it in a tangible way of thinking about this. So if you have a system and you're going to put a step function in there, because it's a resistive plus capacitive kind of system, and you put a step function in there, it's not just going to like go up and then go over like this, right? What's going to happen is that there's going to be this slew rate you got to worry about, so it's not going to be instantaneous. But also, if your system is border unstable, like it has a really small phase margin, then what can happen is that your system can actually ring before it settles down. Okay, does that help you understand?
And so are those like the characteristics of whatever that amp would be doing?
Yeah, exactly. Yeah. So this is going to be the output of that amp. It's going to ring first before it settles down.
The output.
Yeah. So if you send it in a step, it'll ring if you have a very small phase margin. If you have a large phase margin, it'll do something like this. It won't ring. It'll just gradually go up there. And typically that's what happens, unless you have a system that's kind of unstable or slightly towards unstable. But these are stable systems. But does it ring or not? Is a question. Okay. And again, this is for second order systems. Okay? First order systems are just going to be exponentially, gradually increasing to that value. If you have a second order system, you can have the possibility of ringing before you get there. Okay, so here's the third order system, like this. That's the form it takes. And you can see it's clearly third order because if you multiply all this out, you'll end up with a system that looks like this, where you have this third order down here. So, but again, at DC, in this particular case, it's at T0. When frequency gets very large, you end up with something that looks like that. And here, as omega increases, this polar plot approaches 0 along the imaginary axis. So, like along this imaginary axis right here, this value starts going down this direction, and this value starts going up that direction. Okay, and then so what happens is that it'd be cool if we had an animation of this, but you know, you're starting off with something like this, right? And then what happens is that when this whole lobe starts going up like that, it starts going around, and then it can include your t equals negative 1 point, which is what happened here. So this is what it looks like when it finally closes at. And in this case, it's an unstable kind of system. Okay. Okay, so let's look at gain margin right here. So gain margin is the reciprocal of this at the frequency for which the phase shift is 180 degrees, and it's another measure of stability. So graphically, it looks like this. So here's the magnitude at a particular frequency here when the phase shift is at 180 degrees. And the phase shift, I'm talking about the phase of t. When this phase of t is negative 180 degrees, that's the magnitude of that point. And it's like when both of these cross right here. And here's your t equals negative 1. And so that distance right here is the gain margin. And that's the reciprocal of that. Okay? And a lot of times it's expressed in decibels. Okay, so here it says if the magnitude of t of j omega is increased by a factor to or exceeding the gain margin, then the closed loop system becomes unstable because the Nyquist plot then encloses the t equals negative 1 point, which is right here. Finally, process that. Okay, so let's look at stability from the Bode plot. Okay, so here is a plot of loop gain A beta, and here's the plot of the phase right here. And so what you want to do is to find gain margin and phase margin, you do this. So gain margin is determined by identifying the frequency at which the phase shift is 180 degrees. Okay, and so when you're doing phase margin, once it hits 180 degrees, and remember this line right here is the same as this one right there. So if you go straight up like that, the distance between here to here is your gain margin. That's for that. For your phase margin, that's determined by identifying at what frequency your magnitude of t is equal to 1 or 0. That's this right here. So here's t, A beta. That's equal to 0 right here, 0 decibels. So that's this piece right here. So need them together. Okay, that's phase margin, that's gain margin. Okay. Okay, so as an example, let's look at a system that looks like this right here. Okay. So in this particular case, here at 3. Well, actually, let's do this one first. So at 1.2 mrads per second is right here. So this is 1.2 megarads per second. That's that value. The magnitude of the loop gain is unity, and the corresponding phase shift is 145 degrees. So the phase margin is given by this 180 degrees minus 145, which is 35 degrees. Okay, so right here, that right there is about 145 degrees, and that's where they're getting that from. And of course, that's where this is like 0 decibels, and that's where you get this line right here from. And that happened at 1.2 megarads per second. Okay, so that means that the amplifier can tolerate the additional phase shift of 35 degrees before it becomes unstable. And that means that graphically, this piece right here is like 35 degrees. It's like the 180 minus the 145, that's 35 degrees. So this could like move over another, 35 degrees before it starts getting unstable. Okay, that's that part. Oops. Okay, now this part right here, at 3.2 megarads per second, the phase shift is exactly 180 degrees, right? And the corresponding magnitude of the loop gain is 17 decibels. Phase margin is given by 17 decibels. Okay, so at this point right here, you want to go up to right here. This piece right here is at 17 decibels. That's how you're getting your gain margin. Okay, and that's where you get that when this phase is at 180 degrees. Okay. So in this case, the amplifier gain must increase by another 17 decibels before the amplifier becomes unstable. Okay, so you get it in terms of phase or in terms of amplifier gain. Okay, another way of looking at this, like the same thing, is doing this sort of graphically. So instead of plotting A beta, like here, we're plotting A beta versus frequency. Here you're going to break it up in two, right? You're going to say, well, this 20 log A beta is really like A minus 1 over beta, right? That part right there. And we know that beta is usually constant, so this 1 over beta, let's just plot this out. So in this particular case, we have this right here at, so let's look at these frequencies. So you have 10 to the 5th, 10 to the 6th, or 3, 10 to the 6th, and 10 to the 8th. That's like right here, here, and here. Okay, and so we're looking at all those, and at this particular frequency, we're going to set these two equal together, because once they're equal, right here, that means they're equal to 1. Right? I'm sorry. So the magnitude of those together equal 1 at that particular at that particular frequency. Okay, and that's why this is 1 over beta right here, and this is your log A right here, and at that point they equal to 1. I mean, at that point they're equal. So that's the point you're concerned with, and that's at 80 decibels. You have another one at 50 decibels, and another one at 0 decibels over here. Okay, so assuming feedback is independent of frequencies, for 1 over beta equals 80 decibels, this phi of m equals 85 degrees, and you can see that your amplifier is stable, right? For 1 over beta equals 50 decibels, your phi is 15 degrees, and it's still stable, but it's going to have some significant overshoot or ringing. Okay? if you send a step response. Now for 1 over beta equals 0, this right here, your phase margin is now negative 45 degrees, right? And this is clearly unstable. So that just means that it's going to blow up. It's going to be well beyond overshoot. Okay, and that's where you're getting your 85, your 15, and your negative 45 right here. Anything after this is totally unstable. Over here, you're getting closer and closer to stable, but you can clearly see you have some phase margin left, and you have some gain left to play around with before it becomes unstable. Okay. Right on time. So, any questions? Okay, great. Okay, so that concludes the material for chapter 11. And so on Friday, we'll start chapter 12. We'll have a practice exam this weekend, and we'll go over on Sunday. And then you have like a whole week before the, a week and a half now before the exam on Friday of next week.